Section 8.2, Z-test for a mean. The Z-test is a statistical test for the mean of a population. It can be used when n is greater than or equal to 30, or when the population is normally distributed and sigma is known, population standard deviation. All right, so this formula for Z-test should look familiar to you because it's just a matter of taking your sample mean minus that hypothesized population mean divided by your population standard deviation, and then that needs to be divided by the square root of your sample. Okay, now when we're working through these problems, we've got those 5 steps we have to follow. Our first example, in Pennsylvania, the average IQ score is 101.5. The variable is normally distributed, and the population standard deviation is 15. A school superintendent claims that the students in her school district have an IQ greater than the average of 101.5. She selects a random sample of 30 students and finds the mean of the test scores is 106.4. Test the claim at alpha equals 0.05. There's a lot of stuff going on here, so we're going to go step by step on identifying the pieces of this puzzle. All right, now the first step that we need to do is to state the hypotheses and identify the claim. In order to do that, we need to say, okay, so the null hypothesis, we go H sub 0, is our mean, and they said that the standard population mean was 101.5. Okay, so that is our null hypothesis. Now the alternative one is that she's saying her students are better, have a higher IQ. So her claim is that it's greater than the 101.5. This is what the superintendent is saying, so that is where we identify the claim. Okay? Now, the next piece is to find that critical value. Here is we need to identify what our alpha is. So the researcher has decided, or in this case, the superintendent has decided that the alpha is going to be at 0.05. This superintendent wants to have that minimum error of 0.05. Now, because we're looking at a greater than idea, just remember we're talking normal distribution, we want greater than this value, so we're looking at a right-tailed test. Okay? Since we know that it's a right-tailed test, now we need to go figure out the critical value. This is where you go to your Z table, and we're looking for that alpha of 0.05, but wait a second here. 0.05. And we've got one closest to 1.65. Okay, so our alpha helps us figure out. We use the alpha value to come up with our critical value of 1.65. Notice because it's a right tail, it's going to be that positive value, so 1.65. Now, going back to the process, we now need to complete the test value, our Z value, okay? That's x bar minus mu divided by sigma, divided that by the square root of n. Okay, so our test value is going to be that 106.4. That comes from the superintendent's value minus what our population mean was. Divide that by 15. That's how sample, that was our standard deviation. Divide that by the square root of our sample, which was 30 students. Okay? Get that typed into your calculator. You can make sure you put in a set of parentheses, and you should end up with an answer of 1.79. Okay, now this is our test value, our Z value. Now that we have our critical value and our Z value, step number 4 now says make that decision. You'll notice that our test value fell within our critical value, our critical region here. Because that is the case, we are going to reject the null hypothesis. It fell in that critical region, we reject the null hypothesis. So to fill in that blank, it's reject. Okay? Reject null. Okay. Now, the last piece of this is then to come up with a summary statement. So you would say that there is enough evidence, so you would type in enough evidence to support the claim that the IQ of the students is higher than the state average IQ. Okay, step 1 through 5 gets you to that result. Then you can identify the statement there. Okay, another example, or something to consider. In this example, the difference is said to be statistically significant. However, when the null hypothesis is rejected, there's always a chance of type 1 error. In this case, the probability of type 1 error is at most at 0.05. That's the alpha that researcher identified. She wanted to be 5% sure of an error. Okay, or in other words, 95% confident that her results were significant. Okay, moving on to another example dealing with SAT tests. For a specific year, the average score of an SAT math test was 515. The variable is normally distributed, and the population standard deviation is 100. The same superintendent in the previous example wishes to see if her students scored significantly below the national average on the test. She randomly selects 36 student scores, as shown. At alpha equals 0.10, is there enough evidence to support the claim? Okay. Now, we need to first identify the hypotheses and state the claim. Since the superintendent is wanting to look at that population mean, our null becomes what that population mean was. Now our alternative hypothesis becomes what she said she wanted it less than. She wanted to see if the mean was less than that. So we're going to use a less than 515. Because she was trying to prove that claim, or this statement, we're going to call that the claim. Also make a note of the fact that this is a less than. So when we're looking at our graph here, we're looking at a less than situation. We're looking at a left-tailed test. Okay? Now, step 2 says we need to identify the critical value. Okay? The researcher told us we wanted an alpha value of 0.101, and we already talked about it being a left-tailed test. Now we need to identify that critical value. In other words, we want to know when this has an area of 0.10. Go to your table, and we're looking for 0.10. Looking in my table, this is table E, 0.10. Right in this area it looks like. So I'm looking at negative 1.28 is probably closer than the other one. So we'll use that. So my Z value becomes negative 1.28. Okay. Now, step 3 is we need to calculate our Z test, and we're going to use our z-test. We need x bar minus mu divided by sigma divided by the square root of n. Now, if you recall, this data is actually a list of whole bunch of numbers. It did not give us the mean of that sample. What we're going to need to do then is to enter in all of these numbers into our calculator under stat and list. That way we can then get that average. Another option would be just to add up all of these numbers and then divide by 36. Either option, that is where we're going to go next. I would suggest that you pause the video so you can enter in those values. Now that I have all the numbers entered into my list, stat, calculate 1 var stats. I put that into list 1. Go down to calculate. And now I can get my x bar. In this case, we want to use to 3 decimal places, so 509.028. X bar 509.028. I've got all the pieces I need now to type into the formula for my z-test. Minus my mu, which was 515, divided by my standard deviation, 100, divide by how many are in my sample. You can look on your calculator, that gets you 36, where we knew that it was 36 students already. Type that into your calculator into one step, and I get an answer of negative 0.36. Okay? Recall that in order to get into our critical region, it needs to be less than negative 1.28. Our number is negative 0.36. It's in this area. Okay, so it's in the non-critical region. Therefore, we do not reject the claim. Okay? So we do not reject the claim. Since the test value falls in the non-critical, the decision is to not reject the null hypothesis. Then, in summary, there is not enough evidence to support the claim that the student scored below the national average.